astronomers may have detected a new type of object within the Orion Nebula. Serpens is a well-known star-forming region. Imagine if I told you that the James Webb Telescope recently uncovered something in space that defies expectation? And not just one or two occurrences, but several structures of this nature. NASA recently identified 6 massive galaxies through data released by the James Webb Space Telescope. Scientists are puzzled because these findings might require a revision of existing theories. Let's explore what has been discovered. 1. Gigantic ancient galaxies. Gigantic ancient galaxies against an otherwise typical backdrop. 6 intensely red points of light were observed by the James Webb Telescope, and these are no ordinary points. They are, in fact, some of the earliest and largest galaxies ever detected, dating back up to 13.3 billion years. These 6 points were so red that they must have formed just a few hundred million years after the Big Bang, contrary to previous assumptions. Scientists previously believed it took much longer for the first stars and galaxies to emerge, but these ancient galaxies were already substantial and bustling with star formation shortly after the Big Bang. One of these groundbreaking galaxies is 1 trillion times more massive than our Sun and 10 times the size of the Milky Way. That's colossal. Ultimately, this discovery has unsettled the scientific community because the universe may not have begun as we once thought, and the so-called dark ages of the universe might not have been so dark after all. 2. New findings in exoplanet molecules. Astronomers have long been focused on finding an exoplanet with the potential for life. Among many candidates, K2-18b stands out as a promising one. Why? For starters, water vapor has been detected in its atmosphere. Recently, the James Webb Telescope identified carbon-based molecules like methane and carbon dioxide. So yes, K2-18b could have a hydrogen-rich atmosphere and an ocean of water, ideal conditions for life. Additionally, there was even a detection of dimethyl sulfide. Guess who produces that on Earth? Living organisms. I'm sure you can infer the implications. 3. Origins of the cosmic web. Astronomers using NASA's James Webb Space Telescope also observed 10 galaxies aligned like a string just 830 million years after the Big Bang. That's like finding a childhood photo of the universe. Why is this important? Because these galaxies shouldn't have existed at that time based on our current understanding. It seems our models were somewhat flawed. Moreover, this galaxy string is about 3 million light-years long and is anchored by an extremely bright quasar, which is a galaxy with a massive black hole at its center. This line of galaxies might eventually evolve into a massive cluster similar to the Coma cluster in our cosmic neighborhood. 4. Early supermassive black holes. You likely know that black holes grow by consuming nearby stars and clouds of gas and dust. Thanks to the James Webb Telescope, scientists have now observed supermassive black holes in the early universe, even before they had much time to feed on their surroundings. The telescope captured the most distant black hole ever seen in X-rays, located in a galaxy known as UHD-1. The astonishing part? UHD-1 is 13.2 billion light-years away from Earth, meaning we're observing the black hole as it was just 470 million years after the Big Bang. This black hole has an estimated mass between 10 million and 100 million times that of the Sun, which is mind-boggling when you consider it's comparable to the total mass of all the stars in its host galaxy. 5. Horsehead Nebula. The Horsehead Nebula, also known as Barnard 33, is about 1,300 light-years away. Thanks to the Webb Telescope's instruments, astronomers have been able to observe the fine details of the illuminated edge of the Horsehead for the first time. It formed from a collapsing interstellar cloud and shines because of a nearby hot star. The surrounding gas clouds have mostly dissipated, but the distinctive pillar shape made of dense material remains intact. Scientists estimate the Horsehead has around 5 million years left before it begins to fade away. The telescope has enabled tracking of how dust particles are swept away from the cloud as they're evaporated by UV light, creating intricate patterns. 6. The remnants of a supernova. Then there's Copia A, the remnant of a star explosion 11,000 light-years away that occurred around 3,140 years ago in the Copia constellation. We can still see its aftermath today. Astronomers are particularly intrigued by the warm dust, which plays a significant role in planet formation and life. Most of this dust is thought to originate from the heavy elements expelled by supernovae. Thanks to the James Webb Telescope, we can now see tiny fragments of this debris made up of sulfur, oxygen, argon, and neon, glowing in beautiful orange and light pink hues. The dark gaps in the image are caused by these tiny fragments piercing through the gas, leaving a cosmic trail of bullet holes. Additionally, light echoes where the original light of the supernova is absorbed and reprocessed as infrared light by the surrounding space material have been observed. 7. A star-forming region in the Serpens Nebula. Thousands of miles away lies the Serpens Nebula, about 1,300 light-years from Earth. This region, spanning approximately 16 trillion miles by 11 trillion miles, is where many young stars are emerging. NASA's James Webb Space Telescope has uncovered several unusual features in this nebula. Thanks to its observations, astronomers have discovered aligned protostellar outflows, jets of gas expelled by newborn stars interacting with the surrounding gas and dust. These outflows are all aligned in the same direction, a phenomenon never seen before. It also revealed the Bat Shadow, a planet-forming disk that appears to be flapping. Impressive, right? 8. Unseen features in the Milky Way's center. Additionally, we're gaining much more information about our galaxy's dense core, all thanks to the James Webb Space Telescope. The telescope's near-infrared camera recently captured the most detailed image of the Sagittarius A* region, located around 300 light-years from the Milky Way's central supermassive black hole. This image reveals approximately 500,000 stars, and some truly enigmatic structures have emerged, leaving astronomers puzzled. I'm referring to needle-like structures in ionized hydrogen that defy known patterns and are much larger than initially thought. There's also a cluster of protostars, stars still in the process of formation and accumulating mass, spotted in the image. 9. Massive planets. If you're into space, you've probably heard of massive, no, not the sandwich. I'm talking about Jupiter mass binary objects. These are fascinating, free-floating planetary mass binary systems in the Orion Nebula, about 1,350 light-years away. The James Webb Telescope discovered around 40 of these massive systems, and they are unlike anything previously observed. Each one consists of two parts, like a double-planet system, with masses ranging from 0.6 to 14 times that of Jupiter. They are not bound to any stars. They drift freely. Astronomers used a powerful telescope called the Carl G. Jansky Very Large Array to detect radio waves from one of these systems, known as Jumbo 24. The steady radio signals are emitted from both parts of the binary system, which is remarkable because these massive objects shouldn't form or remain together as binary systems. 10. Analyzing star formation in depth. Scientists have always been curious about star formation, but stars are born in dense clouds of gas and dust, right? Typically, dust blocks most visible light, making it difficult to see. However, James Webb's infrared capabilities cut through that dust and reveal never-before-seen details. For instance, the Rucci complex, only 390 light-years away, was captured in a frozen-in-time image featuring around 50 young stars, many similar in mass to our Sun. Without James Webb, the image would be black. What's astonishing is that the telescope also captured dozens of young low-mass stars along with the high-speed streams of gas and particles they emit, illuminating surrounding clouds of molecular hydrogen. 11. The concentric circles of the Ring Nebula. Then there's the Ring Nebula, also known as M57 in the Lyra constellation. It's one of the most striking planetary nebulae, located about 2,500 light-years away. The James Webb Telescope has revealed incredible details about this nebula. The ring itself comprises around 20,000 clumps of molecular hydrogen, and the inner region is filled with superhot gas. The main shell features a thin ring of carbon-based molecules called polycyclic aromatic hydrocarbons. That's a complex term, but it indicates enhanced emission from these molecules. What's unique about M57 in these images are the 10 concentric arcs beyond the main ring. Astronomers believe these arcs were formed near the end of the nebula's life cycle. In the future, M57 will become even brighter and expand until it disperses, leaving behind only a faint, dim white dwarf star in the center. 12. Investigating the atmospheres of exoplanets. The James Webb Telescope has provided unprecedented insights into exoplanet atmospheres. A remarkable case is the analysis of the atmosphere of WASP 39b, a hot Saturn-like exoplanet about 700 light-years away. JWST has detected a range of molecules, including carbon dioxide, water vapor, and even sulfur dioxide, a compound previously unseen in exoplanet atmospheres. The sulfur dioxide detection suggests intricate atmospheric chemistry driven by high-energy processes. This discovery is vital as it enhances our understanding of the atmospheric composition of exoplanets and might provide clues about the climatic conditions on these distant worlds. 13. Reconstructing early galaxies. JWST has also shed light on the formation of early galaxies by examining their structures. Notably, the telescope observed the distant galaxy HD1, which dates back to just 330 million years after the Big Bang. HD1 is remarkable due to its high rate of star formation and a mysterious population of massive stars. Researchers are intrigued by HD1 because its characteristics challenge existing galaxy formation models, suggesting that the early universe was more dynamic and complex than previously believed. These findings provide critical insights into how galaxies like our Milky Way might have evolved over billions of years. 14. The complexities of stellar nurseries. Stellar nurseries, regions where new stars are born, have been extensively studied by JWST. One fascinating case is the area surrounding the massive star-forming complex NGC 2264, also known as the Cone Nebula. JWST's detailed infrared observations have unveiled intricate structures within this nebula, including detailed views of young protostars and their surrounding disks. These observations have provided a clearer picture of how stars interact with their environment and how the surrounding gas and dust influence star formation. The complexity and variety of these structures help astronomers understand the diverse processes involved in star birth. 15. The enigma of cosmic dust. JWST has also addressed the mystery of cosmic dust, which plays a crucial role in star and planet formation. One notable finding is the observation of dust in the galaxy GNZ11, one of the most distant galaxies observed by the telescope. Discovering dust in such an early galaxy challenges previous assumptions that dust only formed in later epochs. This finding suggests that the processes responsible for dust creation and distribution were active much earlier in cosmic history than previously believed. Understanding the origins and distribution of cosmic dust is essential for comprehending the evolution of galaxies and the formation of planetary systems. 16. Observing star birth in the Orion Nebula. The Orion Nebula, one of the most studied star-forming regions, has been examined in new detail by JWST. The telescope's observations have unveiled finer details of the star-forming processes within this nebula, including the detection of new, previously unseen protostellar jets and outflows. These high-resolution images offer insights into how young stars influence their surroundings and how they interact with the surrounding gas and dust. The observations also highlight the role of magnetic fields and turbulence in shaping star formation within this region. 17. The dynamics of black hole accretion. JWST has provided fresh insights into the dynamics of black hole accretion, the process by which black holes grow by attracting surrounding matter. Observations of the quasar J0313-1806, one of the most distant quasars known, have revealed detailed structures in the accretion disk surrounding its supermassive black hole. These observations offer a glimpse into the early growth phases of black holes and their role in galaxy formation. The data also help scientists understand the feedback mechanisms by which black holes influence their host galaxies, impacting their growth and evolution. 18. The evolution of spiral galaxies. JWST observations have also provided new information about the evolution of spiral galaxies. A notable example is the study of a distant spiral galaxy known as M100, which has been observed in unprecedented detail. The telescope has revealed intricate features of the galaxy's spiral arms and its central bulge, offering insights into how spiral structures develop and evolve over time. These observations are crucial for understanding the formation and growth of spiral galaxies, which are among the most common galaxy types in the universe. 19. Discovering new Kuiper Belt objects. While JWST primarily focuses on distant celestial phenomena, it has also contributed to our understanding of objects within our own solar system. Recent observations have identified new Kuiper Belt objects, KBOs, including some with unusual orbits and compositions. These discoveries enhance our knowledge of the outer reaches of the solar system and provide clues about the early conditions of the solar nebula from which our solar system formed. Studying KBOs helps scientists understand the composition and dynamics of the outer solar system. 20. Analyzing the structure of early universe galaxies. JWST has also explored the structure of galaxies in the early universe, offering new insights into their formation and evolution. Observations of the galaxy SMACS J0723.3-7327 have revealed complex structures and interactions among its constituent galaxies. The detailed images show how these early galaxies merged and formed larger structures, offering a glimpse into the processes that shaped the universe's large-scale structure. These findings help astronomers refine models of galaxy formation and the growth of cosmic structures. 21. Hidden structures in the Magellanic Clouds. The Magellanic Clouds, two irregular galaxies near the Milky Way, have been studied in greater detail by JWST. The telescope's infrared observations have revealed hidden structures within these galaxies, including regions of intense star formation and complex interactions between the clouds. These observations provide new insights into the processes driving star formation in irregular galaxies and help scientists understand the role of galactic interactions in shaping the evolution of these nearby systems. 22. Searching for life in icy moons. JWST's capabilities have also been extended to studying icy moons in our solar system, such as Europa and Enceladus. The telescope's observations have focused on the surface and subsurface features of these moons, seeking signs of potential habitability. Data from JWST will contribute to our understanding of the conditions on these moons and the possibility of life existing in their subsurface oceans. This research is part of a broader effort to explore the habitability of celestial bodies within our own solar system. 23. The interplay of galaxies and dark matter. JWST observations have also contributed to our understanding of the interplay between galaxies and dark matter. By studying the distribution of dark matter in galaxy clusters and comparing it with the visible matter, scientists are gaining insights into the nature of dark matter and its role in shaping cosmic structures. This research is crucial for understanding the fundamental properties of dark matter and its impact on the formation and evolution of galaxies. 24. The formation of planetary systems. Finally, JWST has provided new perspectives on the formation of planetary systems. Observations of protoplanetary disks around young stars have revealed detailed structures and processes involved in planet formation. The telescope's infrared capabilities allow scientists to study the composition and dynamics of these disks, providing valuable information about how planets and planetary systems form and evolve. This research enhances our understanding of the origins of planetary systems, including our own.